Good morning. My name is Luke Huber, and joining me today is
Caden Soleil,
Zach Carpel,
Josh Cowell,
and Cade Ing.
and today we will be talking about our Baffled Boys heat exchanger. So to make this all work, it was a team effort, driven first off by Zach doing a lot of the MATLAB calculations as well as a lot of the CAD drawings. Josh and Caden then stepped in next and did a lot of the ANSYS simulations, with Josh focusing on the contour plots and Caden doing a lot with the mesh studies. Finally, myself and Caden here, we did a lot of technical documentation to really bring everything together here at the end. So the task at hand was, from a client, we were given certain requirements we had to meet, given a mass flow rate, inlet temperatures, outlet temperatures, an overall heat transfer coefficient range, and the amount of shell and tube passage you could have, and a given length that we had to stay within. So we were trying to optimize based on all these different things and accounting for cost within. So to start off, the effectiveness NTU method is a huge part of any heat exchanger analysis. What makes this so crucial is that you can do all these calculations of effectiveness based strictly off of the inlet temperature. And so it limits some of those iterations that you would normally have to do with the log mean temperature difference and other calculation methods. You get rid of some of those iterations and can get straight to your efficiency and effectiveness, which then can let you optimize doing different correlations to figure out if you want cross flow, parallel flow, counter flow, and how you want to set up your heat exchanger. So now, diving into the analysis, the first thing we look at is this effectiveness NTU method, which is largely driven by our heat capacity rate, which is seen as C. In this case, C min is our crucial one that we're looking for. So there's a cold fluid and a hot fluid, which are both represented by these C values, and the lower one is what's going to drive our max heat rate. So then we use this value to then correlate it with our NTU, with our effectiveness, to then derive different correlations, as mentioned earlier, with some of these crucial geometries that really help us to make easy adjustments to figure out how we want to best make our heat exchanger. Talking a little bit more about these calculations now is going to be Zach Carpel.
Awesome, thanks Luke. So first up we have some graphs here, just some results from MATLAB. You can see how UA increases with all three of these geometric parameters. Of course, if you increase any of them, the area will increase, and so UA will increase as well. Here's just a PDF CAD drawing of the heat exchanger of our final design. You can see we have 196 tubes there arranged concentrically inside of that shell. The justification for why this heat exchanger, why is this design the best? Well, we had 6 parameters we were looking at. We had 6 nested for loops to iterate through tens of millions of iterations. For the heat transfer calculations to actually see what's going on in each exchanger, we started with the internal convection coefficient. We had one correlation for laminar, one for turbulent. Then moving on to the outside convection coefficient, things got a little hairier here. We first went with the cross flow over a bank of tubes correlation, as we believe this would be the most accurate if cross flow was induced by baffles. However, we weren't able to simulate hundreds of tubes and the baffles in ANSYS, so we changed things up and also did calculations for axial flow through an annulus. We calculated UA using wall resistance, fouling, and the convection coefficients. We made sure to limit U to not be over 1700 as mentioned in the textbook. To make sure that our model matched up with real world physics, we ensured to use if statements around every single equation to make sure that all of the conditions for that equation were met before we used it in the code. Looking at the economic side of things, we had 104 million total design, which is a lot. And the best design out of all of these was the one that had the lowest equivalent annual cost. This is just a way to quantify the cost over the entire life cycle of the product. Ultimately, the client is going to be financially motivated, and so he's going to pick the exchanger that is the cheapest for him and for his company. Next up, Kate and Josh are going to talk about the simulations they did on our exchangers.
Thank you, Zach. So we started our simulation process by making the geometry in SolidWorks. That was really crucial for us because as we got new numbers for Zach, we were able to easily iterate that and then get another simulation running. We did our meshes using ANSYS surface meshing, and one really key thing for us was to have inflation layers. That we were able to increase our boundary layer accuracy and really see how those boundary layers were developing. And our total cell count was 21.73 million cells. We used a pretty standard double precision solution using energy and the viscous SST K omega model. And with our materials, we decided to make it a little more accurate. We wanted to have 2 different densities for both the hot and cold water as we're giving the 2 different temperatures, as well as getting book values for the copper and steel shell. And then our boundary conditions, we decided we wanted to have mass flow inlets at the designated temperature as well as pressure outlets. And then finally, we are solving for heat transfer in this, and so we generated reports for both the hot and cold inlet as well as hot and cold outlet. And we used hybrid initialization and decided to calculate for 400 iterations. However, it was able to converge after only 111 iterations. So you can see on those charts right there that that is the scaled residuals as well as the 4 different heat transfers we solved for. And to obtain our final number, we had to take the difference between the heat transfer of the outlet and the inlet for either the hot or cold fluid. And then also using that, because of the way we simplified our geometry into only one tube, we had to multiply by a scaling factor. We kept the same cross-sectional area of both the hot and cold fluid. However, we also had to account for the big difference in surface area, so we ended up multiplying by a scale factor of about 14.
Yeah, so and onto the results between our MATLAB calculation and our ANSYS. The heat transfer rate we were able to get down to 14% as well as the effectiveness. NTU stayed at about 43%. So I would say it's a pretty good simulation that we were able to get compared to the hand calculations. We're all pretty proud of that. So on to the plots. I showed 2 plots here, but we have plenty that we'll be able to show in the paper. But as you can see, we have a pressure versus position and then a mass flow versus position, which are pretty clear correlations there that you can see in the plots. So let's go on to the MATLAB versus the ANSYS. So going back to kind of those numbers that we had before, there were some discrepancies that we saw. So some reasons for that were the hand calculation assumes a uniform velocity, and it does not account for recirculation and mixing that the ANSYS does. The hand calculation also assumes that there is ideal flow, which the ANSYS actually is able to calculate a more realistic flow, which is why it takes so much time and computational energy. And then also for the hand calculations, unfortunately, we were limited to any correlation that Zach was able to find. He did a great job finding as many as he could, but we're still very limited to how we can compare to ANSYS, because ANSYS is able to use these very complex energy and Navier-Stokes equations. And of course, the property differences between the flow is also a factor. And of course, using one conversion factor between the two is not a great method as well. So onto some contour plots. We have some pretty nice ones that you'll definitely be able to see in the paper as well. But I'll go ahead and hand it off to Kate.
Yeah, so getting into some of the limitations and considerations for this project, our biggest challenge along the way of completing this project was the available computational resources we had to be able to complete the complex fluent simulations that we wanted to run. Initially, our goal was to be able to run simulations for that full bank of tubes with the baffles creating that crossflow, but this just proved to have too many nodes and just to be too complex for us to be able to run effectively on our computers. Additionally, we were a little bit limited in our research findings for equations for the friction factor across a bank of tubes, which slightly altered our final value for the pressure drop. Finding equations for axial flow through bundles of tubes would have also improved the overall findings and results of our work. Getting into some of the ethical considerations, we wanted to make sure that we considered the environmental impact of a heat exchanger, knowing that a poorly designed and inefficient heat exchanger would lead to increased power usage, which would mean that there is increased emissions, which we would like to minimize. Additionally, we wanted to consider the product life cycle and the death and recycling portion of that, knowing that a large metal heat exchanger is difficult to dispose of. And finally, we wanted to be respectful of and responsible for the business or the customer that we were producing this heat exchanger for, and so we wanted to produce a cost-effective solution. In summary, we successfully designed an annular concentric shell and tube heat exchanger. We successfully ran ANSYS fluent simulations to validate our results. And our key result was that we had a difference of 14% between our hand and ANSYS results. And finally, there is a slide of references. Thank you so much.